So our next presentation is ESD protective contactors for optimal test performance, presented by David Skodje. He's a senior custom product engineer at Johnstech International in Minneapolis. The inventor of multiple engineering patents, David has been a member of the Johnstech team for 5 years. David holds a BS in mechanical engineering from Boston University. So please, David, start.
Thank you, Mark. And thank you all for your attention today. I appreciate the opportunity to present. As Mark said, I'm a senior custom products engineer at Johnstech. And today I'll be sharing a presentation that I created with my co-authors, Emerson, Ruel, and Raymond from Analog Devices. And in this presentation, I'll be sharing our qualification process for a new contactor material, which is called ESP, that we've selected for ESD sensitive applications. So Analog provided the impetus for this development. They came to Johnstech with some specific material requirements for a new contactor material that they were requesting to proactively minimize the potential for ESD events in final test. And this new contactor material is intended to serve as a risk mitigation tool to complement existing ESD control methods. And in this presentation, I'll be sharing the qualification process that we used for the material, as well as some background on ESD in final test. So what is ESD and why is it relevant to final test? ESD is the rapid transfer of electricity from between two bodies at different electrostatic potentials. For example, charge could transfer from a human to a semiconductor device. And in that case, depending upon that device's sensitivity to ESD and the intensity of the charge transferred, it could result in damage, which needs to be avoided through control methods. And if the damage does occur, it could either be an immediately identifiable failure or it could be a latent failure. And these failures are very challenging to identify and resolve. So that's really the drive behind this new contactor material. It's an additional tool to mitigate risk. So when a failure is identified, many tasks are triggered. The first step is containing all impacted lots. This includes devices that have been shipped to the customer that are stored in the warehouse, as well as parts that are currently being tested. And these parts will require retest with reliability testing. Another action that's triggered is the process to identify the root cause. And this is not a trivial task because there could be many potential sources that need to be evaluated. And that's why control methods are designed to minimize those potential sources. And production cannot resume until the cause is resolved. The time spent identifying the root cause of this failure would impact the cost of test. It can add machine downtime, it can cause delays to shipments, and it requires repeat testing, which all adds to the cost. So that's why there are so many controls and rules to minimize this risk. Additionally, once the failure mode is identified, the resolution efforts may require a design or process change, which would initiate a change notification process to customers. So an important step in managing ESD is determining the device's sensitivity to ESD. And there are some standard scenarios that are modeled with some different discharge networks. For example, there's the human body model, which simulates discharge from the human to a device. There's the machine model, which simulates discharge from a conductive body to a device, and the charged device model, which simulates discharge from the device itself to another object. And in each case, these tests are completed at multiple voltages, and the highest passing voltage is recorded as the withstand voltage for that particular test. And the lower the withstand voltage, the more sensitive the device is, and the more controls are needed to guarantee mitigation of ESD events. Next, I'll share some examples of some existing controls. So with the sensitivity known, processing and handling requirements can be defined. An important concept is the ESD protected area, which is a location that's designated as safe for handling of ESDS devices based on adherence to the proper procedures and equipment. When parts are not in this area, they need to be stored in ESD protective packaging to mitigate the risk of the events. In the protected area, environmental controls are used, like temperature and humidity, to mitigate risk. Additionally, ionizers can be used to neutralize charge on conductive surfaces. Floor mats and benches can provide additional protection. Also, it's important, as we all know, to neutralize humans. We wear wrist straps when we're handling the devices, specialty footwear and clothing, all to minimize risk. And the ESP contactor material that I'm going to describe in this presentation is selected as a complement to these tools, another tool to mitigate risk for our customers. So with any new development effort, one of the important steps is evaluating market trends to ensure that there's justification for the development efforts. And based on what we've found, we believe that the ESD problem is not going away, and this product will provide value for our customers. So as IC density increases, component sizes are reduced, and the same current is more likely to cause a failure. ESD protection networks can be used to divert current from sensitive components, but these will add capacitance and can't be used in all cases. For example, some performance degradation with RF signal lines, it might not be applicable in those cases. So in general, it's expected that circuit performance will be prioritized over ESD protection. So this means that the controls I mentioned before and possibly new controls like this ESP material will be necessary in the future for certain applications. Before I share the product requirements, I'd like to provide a little more background on ESD. So one important detail is that material properties impact the severity of the event. The lower the resistance of a material, the more charge can be rapidly transferred. And this is evident if you look at the withstand voltages based on the tests I described earlier. Typically with the machine model, the withstand voltage will be lower than the human body model for the same device, and that's based on the lower resistance of that discharge network. Additionally, so based on this, it's very important to ground conductors to prevent this damage. Another concept that's important to understand is where the charge can originate from in the test environment. One source is tribocharging, which is the process by which electrons are transferred from one object to another due to the contact and separation of those two bodies. And friction is another mechanism or way to think of that. And the tendency to gain or lose electrons in that case is based on the chemical structures of the two objects. And in the case of insulators, they will not dissipate the charge through their volume, so the charge can build up on the surface of the insulator. And that retained surface charge can be a problem in an environment where you have moving components and devices sliding on surfaces. And that's why it's important to use ionizers to neutralize charge on surfaces, or additionally, in the case of this development effort, the use of the ESP material to mitigate charge accumulation. Next, I'll share the product requirements. So as I said before, Analog provided the request for this material, and they came with two specific requirements. The first is that the surface resistivity for the material had to be greater than 1 e to the 11th ohms. And the second was that the electrostatic voltage on the surface of the material needed to remain below 100 volts, both before and after a tribocharging procedure that they complete. In addition to Analog's requirements, Johnstech also had some standard contactor requirements, and these were related to electrical performance, manufacturability, and mechanical performance and regulatory compliance. And I'll describe these requirements and how they were qualified on the in the rest of this presentation.
David, quick question. When you say 100 volts after tribocharging, how do you actually measure that? Because from my physics course, I remember you need a cat and a sheet of fleece or something, or how do you do this?
Oh, for their tribocharging procedure?
Yeah.
Yeah, so I'll talk a little bit more about that. I'm actually not disclosing the specifics of the tribocharging procedure, but yeah, in general, you do want to select a material that's maybe similar to one that you'd expect to see in the environment, and tribocharge it for a certain number of cycles, and then measure it with an electrostatic voltmeter. That's the general procedure.
Okay.
Thanks. Okay, so here's an overview of the qualification steps. And these steps don't always occur in serial as shown here. We had some parallel paths, but this is how I'll talk about it in this presentation. So with the requirements defined, we were able to select potential materials that met the requirements based on manufacturer data sheets. And once we had samples in-house, we're able to complete the ESD material tests and then manufacture prototypes and perform testing. So beginning with the ESD material tests, so Analog completed this testing for this qualification process. And the two tests, like I mentioned before, are the surface resistivity and electrostatic voltage tests. And in the case of surface resistivity, as it sounds, is the measurement of the resistance on the surface of a material between two electrodes that are placed on that surface. And I won't be describing Analog's specific procedure, but in general, you can purchase probes that in some cases will have two concentric rings to use a standard area between those two electrodes to give consistent resulting resistance. And the electrostatic voltage is measured both before and after tribocharging procedure, so some kind of mechanical friction or contact between the two objects. And in this case, as you would expect for the materials that are being measured here, the voltage is always higher after the tribocharging procedure. And on the next slide, I'll share some results of testing. So here's a figure that I put together based on data provided by Analog. And on the x-axis, the surface resistivity is plotted. And on the y-axis, the voltage after tribocharging is plotted. I didn't plot the voltage before tribocharging. And I also included the limits for the requirements with the dashed lines. The vertical dashed line indicates the lower limit of surface resistivity, and the horizontal dashed line indicates the upper limit for the voltage. And generally speaking on this figure, the lower left corner is going to be a more conductive material, and the upper right corner is going to be a pure insulator. And Analog was looking for a material that fell within this lower right quadrant. And I've plotted data for ESP and then a selection of other materials that Analog provided that were all being considered for contactor materials. And you can see that ESP fell within the band, and a couple other materials also met both requirements. So multiple materials met the requirements that for the ESD material related tests. And some of those materials were also manufactured into roll contactors, but based on downstream testing, we determined that for mechanical reasons or processing challenges, those were not selected. Additionally, we encountered a material where the surface resistivity passed based on the blank as it was formed, but upon milling into the blank, we found variation in the surface resistivity so we avoided that material. So another very important step in the development of a new material is manufacturability. And Johnstech engineering demands really tight tolerances and high aspect ratios on our contactor drawings to ensure repeatable performance. And for a new contactor material, that can bring in some challenges for operations. So early in the development, we enlisted the support of manufacturing engineering to aid with process optimization. They had prototype parts manufactured that had common features that needed to be evaluated. And based on that, best practices for milling were established, as well as deburring. And we were able to then move forward to make actual prototypes for testing. Another important step in manufacturability is ensuring that compliance to REACH and RoHS are recorded and documented for the material. So another really important step in the development of a new material or new contactor material is test planning. And depending upon the type of development effort that we're completing at Johnstech, we'll execute a different battery of tests to ensure requirements are met. For example, if we were looking at new contact geometry for a roll contact, it would have a very different set of tests than this new housing material, although there will be some overlaps. So what we used is a weighted risk analysis to identify what features and requirements were at high risk, and based on that analysis, we were able to specify what tests were needed and what actions were needed to be taken to qualify the material for use. Also, during this risk assessment, we identified that finite element analysis would be a really useful tool to identify what testing would be needed for the actual physical prototypes. So mechanical strength requirements and stiffness requirements for contactors varies based on applications. Johnstech has a wide range of different configurations that we manufacture our product in, and this is based on customer requirements. For example, different mounting footprints, different contact counts, pitches, clearance requirements on the PCB, handler interface requirements. They all change the overall contactor design, and that changes what strength requirements and stiffness requirements there are for the material. So to confidently qualify this material, we started by looking at over 40 different designs and performing a thickness analysis with a CAD package thickness analysis tool. And it's a simple tool. It just highlights the surfaces based on their thickness. So a red surface will show up, a thin surface will show up as red. And with all those images that are generated and models that are generated, engineering is able to inspect those images, and based on our understanding of the different loading conditions and requirements, we're able to identify where the risks are. And from that, we can easily transition those CAD models into simulation and evaluate where is the highest risk for deflection, where is the highest risk for reaching the material yield strength or within some safety factor of that. And based on that, we were able to specify, all right, what prototypes do we need to manufacture and what load conditions do we need to simulate to ensure that the material is robust. So with our tests planned and our prototypes selected, we were able to perform physical mechanical testing. And it's very important to evaluate mechanical performance over tri-temperature for test contactors because they're required to operate at wide temperature ranges, -40 to 150 C. It's a very broad range, especially when you're looking at a new material, because material supplier data sheets don't often include stiffness and strength details at wide temperature ranges. It's not uncommon to just have data at ambient. So it's really important to perform the testing, to evaluate the performance over life, and also to complete more fundamental material tests related to bending, drop testing, and wear testing. And we found that ESP passed all of the mechanical tests that we completed. Another important test to complete is electrical performance for a new contactor material. And for this testing, we compared ESP directly to our premium roll housing material Torlon 5030. And what we did was we manufactured dimensionally identical roll 100A contactors, and we assembled contacts in them, and we probed the contacts and measured the S parameters with a vector network analyzer. And here I'm plotting the return loss from 0 to 40 gigahertz, which is the amount of signal loss due to reflection. And you can see that both of the materials provide a return loss about -20 dB or better out to 40 gigahertz. And it's important to experimentally verify this performance because, like mechanical performances across thermal ranges, dielectric properties are typically only provided at low frequencies, and there can be some variation across a wide band. With the same test vehicles described on the previous slide, we can also, here's a plot of insertion loss, which is a measure of how well the signal is transmitted through the contact. And you can see that both materials have insertion loss better than -1 dB to 40 gigahertz. And for the majority of the range, even better than 0.4 dB, -0.4 dB. And finally, here's a plot of the crosstalk for the same test vehicles, which is the signal loss due to neighboring contacts. And both of these performed better than -20 dB to 40 gigahertz. So in addition to testing that Johnstech completed, Analog also completed testing. As I mentioned before, they completed the 2 ESD-related material tests. But they also completed an electrical correlation testing, which compared the standard Torlon housing to the new ESP material, and they found passing correlation. They also completed visual mechanical qualification, which passed after running devices for the ESP contactor. And they expect a high volume production fan out after the manufacturing validation has been accepted. Okay, so based on the testing that we've completed, both at Johnstech and Analog, we found that ESP has met the performance requirements that we specified at the beginning of this project. So we think it's ready for ESD sensitive applications. So far, the development that we completed, all the testing was done on our roll products, on roll 100A and roll 200. But based on the good performance, we plan to expand it to other technologies in the future. So with that, I want to thank you all for your attention today. Thank my co-authors and everyone for the opportunity to present. Are there any questions?
David, thank you very much. Yeah, we have a couple of questions. The first one is about leakage. Have you measured the leakage between the two contact points with specific contact pitch, like 400 micron or so?
Yes, I know that a leakage test was completed. I'm not sure. I think it was at 500 micron pitch. I don't know the actual value off the top of my head, but that testing was completed. And if someone has a specific question on that, they can contact me or someone else at Johnstech, and we can get them that information.
Second question is about whether you did any investigation between the interaction between the plunger and the test socket. Is it possible to build a plunger with the same material as the test socket material?
Mm-hmm. That's a good question. You know, we did not. That was not in the scope of this development effort. And I'm not an expert on the all the material requirements for the plunger itself, but I'm not sure why that would be, what would prohibit that.
Okay, then next one, how does this material react at temperatures in terms of TCE? And does introduce contaminants like oils or solvents change the surface resistivity or conductivity of the material? So basically, is there any issue if you have some oils or solvents contacting the material?
Yep. So as far as the thermal coefficient of expansion, we did perform a lot of testing on the material stability, and we found that it meets the requirements for testing that we specified. As far as oils and solvents, we did not perform testing on with oil submersion or solvent submersion.
Does this material attract water during cold temperature, like at minus 40 degrees?
We didn't encounter any challenges. We did the minus 40 degree life cycle testing, and we didn't see any hydroscopic effects or any issues from that.
So is it similar to the Tolon 5530 in terms of hygroscopic nature, or can you say something about this?
I don't know off the top of my head the specific comparison. I think it may be. I can't. I don't want to guess, basically. So I won't give a specific number on that right now. But I think it's similar, possibly better, but I don't know for sure.
And do you think that this kind of material or ESD requirement, is that going to stay kind of a niche material, or do you believe it will become kind of mainstream for basically all kind of sockets in the future?
Mm-hmm. You know, I'm not sure exactly. I know that this was a customer-driven request, so I believe that there was some support behind that. What I've in the research that I did, my sources suggested, and I have references on the last slide here if people would like further reading. But the idea was that at least in the short term, I think there's going to be a higher percentage of devices that are falling in the lower withstand voltage range. But I'm not sure if the actual voltage limit is going to continue going down. But I think based on the sources that I cited, there will be more devices falling within this ESDS low voltage classification.
And one more question from my personal experience. I feel, or I know that sometimes it's difficult to really achieve a very high consistency in this material properties over time. That, like, if you have different batches over several months or years, that they really behave exactly the same. Do you have any longer term idea about this already?
Yeah, well, our quality department was obviously involved in this development effort, and we did look at different lots, and we tracked the production dates on those. And I believe it was over a couple years difference in some of the production dates. And we always do, at least if you're talking about the ESD properties, we do our surface resistivity and electrostatic voltage measurement on those to verify that those lots are good when they come in. We have an incoming inspection procedure on the raw material when it comes in. But so far, we've seen consistency from lot to lot based on our monitoring of that.
Okay, thank you.
In conclusion, I'd like to very much appreciate our sponsors who've made this event possible and allowed us to do this without registration charge. Our premier sponsor is Kohu. Our emeritus sponsor is Johnstech. Our honored sponsors are ISC, IWIN, and TSC. Our distinguished sponsors are Backer Hot Watt, Innovative Circuit Engineering, JMT, Nidec SVTCL, R&D Altanova, and UI Green. Our exhibitors sponsors are ELES, MJC, Phoenix Test Arrays, and Smiths Interconnect. So thank them once again, and when you have an opportunity, please thank them. An extra special thank you to Kohu, our premier sponsor, the market leader in test interface solutions for the most challenging applications. Our honored sponsor, ISC, global #1 total test solution provider. And IWIN, the test probes provider for high signal integrity at extremely high speed test. And once again, I would thank all of you for attending and participating in this week. Look forward to seeing you all online the week of October 25th for TestConX China, and then March 3rd through 9, 2022 for our in-person event in Mesa, Arizona. So I wish everybody a good rest of your day. Thank you for your participation.